Namaskaram. Good evening, student. Today we are going to discuss collision. Collisions, which is the topic, belongs to that unit work energy power. Okay, 11th physics. In your chapter work energy power, we have a one important concept, collision. Okay, right. What do you mean by collision? First of all, you have to know what is mean by collision. After that, we will go into that what are the types of collisions, and that collision in one dimensions. Okay, we will discuss later. Collision is a common phenomenon that happens around us every now and then. Okay, you can see every day. For example, you can already you may play that carom board. So carom, billiards, marbles, etc. are the example of collisions. Collision between collision between happens between two bodies. Okay, without or with physical contacts. Collision can happen between two bodies with physical contact or with physical contact. Uh, Without physical contact means in our nuclear physics, there is an one term that is alpha particles. Alpha particle bombard with that nucleus, but alpha particle does not interact with nucleus. Only goes like here and deviate from that nucleus. But that also called as collisions. Okay, so without physical contacts. But we are now only consider about the with physical contact here. Okay, right. In all our collisions, there is a one term is considered. That term is linear momentum. Linear momentum considered in all the collisions. Okay, all collisions process. Linear momentum conserved in all collision process. What is linear momentum? Already we know that we can put P in terms of momentum, that is linear momentum. P is equal to M into B or M into U, nothing but mass into velocity. Okay, linear momentum is multi-product of mass into velocity. Suppose one object has something mass that is 5 kg. Okay, it travels at a speed of 5 meter per second or 5 meter second inverse. Okay, so this is a mass, this is a velocity. Product of this mass and velocity gives the one quantity, that is linear momentum. So linear momentum is not a base quantity, it is a derived quantity which comes from mass and velocity. Okay, if you product that mass of that object with the velocity, you will get momentum for that object, for this object only. Okay, right. So this linear momentum does not change in all the collision process. That means conserved. Conserved means does not change. Okay, we can see in that simulation. Okay, when two bodies collide, okay, collide, there is a impulsive force between these two objects. There is a impulsive force. Impulse mean nothing but collisions. Okay, impulsive force between these two bodies. That object gives a impulsive force on this object. That object gives a impulsive force on this object. Okay, so this object change the momentum of this object whenever collision. This object change the collision of momentum of this object by the collision. Okay. So whenever two bodies collide, there is a impulsive force between these two objects. That is mutual impulsive forces, okay, acting between them during the collision. So first body exert a force on second body exert a force on first body. So this causes a change in momentum. Okay, this causes change in momentum by this object by this object. So momentum means m into v. We have another formula. Why the linear momentum is not conserved in all collision? It's not conserved in all collision. It's not conserved. I will tell you later. By the mathematical derivations and as well as in our simulation, we can imagine that how the linear momentum is conserved in all the collisions. I will tell you later. Yes, good question, super question. I will tell you later. Okay. So linear momentum conserved. Why that quantity conserved in all process? Because already I told you there is a impulsive force between two objects. We have another formula for momentum. That is um, momentum is equal to F dot T. So F dot del T. Okay. Del P is equal to F dot del D. So here I can put P1. This is a change in momentum of first object. Momentum change in the first object by the force of second object. So I can put here F12. So that means the force on the first body by the second body. Okay. Force on that first body by the second body. Another one quantity del P2. So momentum is a vector quantity. We should put in the vector symbol. So this object gives a force F21. That means force on that second object by the 1. This object gives a force F12. Okay. So just remember that how the F12 or F21 denotes here. So this force change the momentum of this body. So del P2 means F21 because this object momentum changes only by F21. This object momentum changes only by F12. So that only we can put here like okay, del T. So which is another formula for momentum. Del P P is equal to F dot T. Okay. Because this is nothing but Newton's second law. In our Newton's second law, F is equal to dP by dt. Yeah. F is equal to ma. In other words, change in momentum by time. If this is directly proportional to force, according to the Newton's second law. So P is equal to F dot T. So according to the Newton's second law, we have another equation for momentum. Okay. Adding these two equations, del P1 and del P2. Here also we can add F1 to del T, F21 del T, because force is vector quantity and momentum is vector quantity. Okay, time is a scalar quantity. Okay, right. So we can take out del T common. Okay. According to the Newton's second law, this force which is equivalent to this force, but in opposite direction. Yeah, you can see the direction. Okay. So F12 means which is opposite to F21. These two forces which are equal but in opposite direction. Okay, by Newton's second law, you can push one object. That object pushes your hand in opposite direction. Okay, right. So F12 equal to minus F2, F21, F12 here and F21 here. So here this time comes to here F12 plus F21. Okay, then here 0. Yeah, which is a total force. So total force means here also 0. Yes, F12 plus F21 because of Newton third law, we got a total force 0. Force is there, but no total force. There is a meaning. There is a difference between no force, total net force 0. Okay, no force means there is no force in that system. Total force 0 means there is some force, but the addition of that force which gives a 0. Okay, that object is at rest. Okay, that means 0. Okay, so 0 into dt del t are 0. So del p1 plus del p2 which is 0. That means del p1 plus del p2 which is equal to 0. Okay, we can take out del common. So P1 plus P2 equal to 0. Okay. We can change the del into D and divide by del T on both sides. So 0 by del T, 0 by anything, 0. But here we can change into del to D, del to D. So differentiation. Okay, which is 0. Why we are included dt? Because it is differentiated with respect to time. All the quantity differentiated with respect to time because time goes on. Okay, so we can compare the some quantity with respect to time because time is an independent quantity. It does not wait for some quantity happens, something happens. It always goes on. But momentum, force, position are always with respect to we can differentiate with respect to time. So that only I put dt here. So d by dt momentum, total momentum is 0. That means in our maths class, you can remember that suppose you have differentiate one constant time, you got the 0 value. Yeah, you can remember in our maths class differentiation. You have differentiate something constant value, you got that 0 for that equation, for that sum. Yeah, that means here constant differentiation constant equal to 0. Whenever 0 appears, that you are done the differentiation that constant term. So here P1 plus P2 is constant. Okay. So in this expression, we have P1 plus P2 is equal to constant. It implies that total linear momentum is conserved. Yeah. We are not going into that particular type of collision. Just we are dealing with that force, time, del P, that only. So we got a P1 plus P2 constant. That means total momentum is conserved with independent of collision types because we have a some type of collision, inertial collision, elastic collision, but here is universal truth, that is linear momentum is conserved in all the quantity. Momentum is a vector quantity. Vector addition has to be followed to find the total momentum. Okay, right. So that only I am saying that total linear momentum is conserved in all process because of this step. Okay, now we are going into that another step. Types of collision. types of collisions. Okay. So in all the collision process, total linear amount of conserved, but total energy concept also we can consider. But the total energy always conserved also, but the total kinetic energy need not be conserved always. Okay, total energy always conserved, but total kinetic energy need not be conserved because of that formula of v square. I can derive it later. Okay, whereas total energy is conserved, but total kinetic energy need not be conserved always, because in some collision process there is some kinetic energy converted into other form of energy. There is a loss in kinetic energy, but in terms of total energy, okay, that means law of conservation energy. Already you may remember that kinetic energy increases, potential energy decreases. Kinetic energy converted into thermal energy is nothing problem, but total energy always conserved. Here also I'm saying that same process, that is total energy is conserved, but total kinetic energy need not be considered always. Okay, because some part of initial kinetic energy converted into some form of energy in some collision process, because impact of collision and deformation occurring due to the collision maybe in general produce heat, sound, light. Yeah, you can here get here is okay, there is some sound. This object collide with this object. Okay, there is a sound. This sound formed by the kinetic energy of this object. Yes, kinetic energy is converted into sound energy, light energy, heat energy. That's only their kinetic energy is less than that initial kinetic energy. Okay, right. So types of collision, we have here two types. One is elastic collision. Another one is inelastic collision. Okay, there are the two types in that collision. One is elastic collision, another one is inelastic collision. Okay, first of all, we will be discussing that kinetic energy. Sorry, elastic collision. Okay, elastic collisions. In a collision, already we say that total linear momentum is conserved. Okay, okay. Here, total kinetic energy of the body is conserved here. Okay, in that elastic collision. That means kinetic, that means total kinetic energy before collision, which is equal to total kinetic energy after collision. Okay, when two bodies collide or bombard, their initial kinetic energy is equal to their final kinetic energy after the collision. Okay, total kinetic energy before collision, which is equal to total energy after collision of the two bodies is equal to the in terms of kinetic energy. The total kinetic energy is also considered in the elastic collision. 2 points very important. One is total linear moment conserved. Another one is total kinetic energy conserved, because before collision total kinetic energy is something, and after collision there is a something total energy, total kinetic energy. They are equal. Okay, this is for elastic collision. Then next, inelastic collision. In inelastic collision, there is one quantity will change. Okay, total linear momentum always considered, but total kinetic energy of the body is not equal to total kinetic energy of the body after collision. Okay, so total kinetic energy of the body before collision is not equal to, sorry, okay, is not equal to total kinetic energy of the body after collision. So this is for inelastic collision. Total kinetic energy before collision is not equal to total kinetic energy after collision. Why? Because there is some loss in energy during the collision in an inelastic collision process. Okay, because you can put in some form, that is total kinetic energy of the first body 10. Okay, bombard, and after that, after collision, it will form into 8. There is a less 2, because these two kinetic energy converted into light or sound or heat. Okay, so that only in elastic collision, total kinetic energy is not equal to total energy after collision, because of there is a loss. We can see in that simulation. Okay, in the simulation we can imagine how the elastic collision is converted, how the whole elastic collision happened, how the inelastic collision happened, how the total kinetic energy is conserved, how the total kinetic energy is transferred into another form of energy. Okay, right, we can discuss later. Okay, so even though total kinetic energy is not considered, but the total energy is always considered. Okay, so that point very important. Total energy considered, but total kinetic energy need not be considered. This is because total energy contains kinetic energy and as well as some other form of energy, heat, sound, light. Okay, so which includes all the losses that takes place during the collision. Okay. So loss in the kinetic energy during collision is transformed into another form of energy. Already I told that sound, thermal, okay, right. So to elastic collision, total momentum is conserved. Inelastic collision, total momentum is conserved. Elastic collision, total kinetic energy is conserved. In inelastic collision, total kinetic energy is need not be conserved. Okay, right. So now we are going to discuss the elastic collision in one dimension. Elastic collisions in one dimension. Okay, elastic collision is one dimensions. One dimension means we have already we are living in that three-dimensional world. Yeah, x, y, z. Some object having that coordinate x and y. But one dimension means one direction. Maybe x direction or y direction or z direction. So here one dimension means one direction. Consider two bodies. Okay, consider two bodies which can say a mass m1, which can say a mass m2, moving in a straight line. This is a straight line. These both object moving in that straight line, this direction. Okay, along the we can take in the along the positive x direction on a frictionless horizontal surface, because friction includes some addition restriction. So we have to add, we have to alert in that situation, that is frictionless surface. Okay, right. So that object has a mass m1. That object has a mass m2. Mass m1, this object has velocity u1. That is initial velocity. Okay. Mass m2 has a initial velocity u2. Okay. This is before collision. Okay. After traveling this direction, these two objects will collide. Okay. Because we have one important consideration, that is the speed of this object is greater than this. So this object will go here and bombard or collide this object. Okay. In later time. So after collision, after collision, they moving in the same direction, that is one direction, x direction, but their velocity changes. Velocity changes. Mass does not change. Yeah. In our universe, one object has something mass, it does not change. Always the same mass everywhere. Now and then. Okay. But velocity changes. So u1 means initial velocity. So here final velocity means we can label it v1. And u2 convert into v2. Okay. Like goes like here. Okay. Why their velocity changes? Because before collision, they travel with respect to their velocity. After collision, this object gives some force into this object, and this object will give some force into this object. Already I told you that whenever two objects collide, their momentum will change. Yeah, already told you. Momentum means mass into velocity. Mass does not change. Then only the velocity quantity will change. That only u1 converted to v1. So that means u1 not equal to v1. u1 is something different. v1 is something different. Maybe 2 meter per second or 2.5 meter per second. Maybe, okay, nothing matter here. u2 is converted into v2. That means the mass m2 has a initial velocity u2, but after collision, the velocity of that second object will change into something, that is v2. Okay, right. So in order to have collision, we assume that mass m2 moves faster than the mass m2. Yeah, because suppose m2 have a larger speed or faster than this object goes like here, this object follows that object only. Yeah, so we consider u1 is greater than u2, then only collision will happen. Yeah, this object goes like that, we can take 2 m meter per second. Okay, why the u2 is converted into v2? Yes, already I told you, that is whenever a object collide, their momentum will change. Yeah, this object gives a force to this object, and this object will go will give a force into this object. This force change the momentum. Momentum is mass into velocity. Okay, mass does not change. Then only velocity change. That only u2 is converted into v2 and u1 converted into v1. Okay, right. So conditions means u1 is greater than u2. This condition for to have a collision. Okay, so m1 faster than m2. For elastic collision, the total momentum of that this collision process will not change. So conserve. Kinetic energy of the two bodies before and after collision also conserved, remains same. So for elastic collision, momentum before collision and after collision same. Kinetic energy before collision and after collision same. Okay. So first of all, we will discuss that momentum. Momentum is mass into velocity. Yeah. For mass m1, it has a velocity u1. So before collision, why mass is does not change? Mass is like is nothing but it contains a matter. Yeah, electron, proton in our bodies. It does not change. So mass is like a changing quantity. It does not change anywhere. Okay. It does not, and it does not depend on that external quantity. Weight is a external quantity. Okay, weight depend on gravity. Your weight here 60 kg, but this 60 kg does not same into that your weight in that Mars in that moon. Okay, because in that planets gravity change. So gravity change means your weight change, but mass does not change. Mass is a basic quantity. Basic quantity that mass does not change for any one object. Okay, right. So mass m1, it has velocity u1. Before collision, momentum m1 u1. Okay, before collision. So that only I can write here bc. Mass m2 u2. Before collision, momentum m2 into u2, because momentum is mass into velocity. Okay. So before collision, we can add these two momentum because of total linear momentum before collision. Okay. So I can label it I, initial momentum. Okay. So we can add into that two momentum here, m1 u1 plus m2 u2. These are all for before collision. After collision, m1 here, u1 transformed into v1, m2 here, u2 is converted to v2 for that mass m1, mass m2. So after collision, final momentum, we can label it pf, because this is the initial momentum, this is the final momentum after collision means. Okay, so pf, which is equal to these two quantities. Okay, so pf means m1 v1 plus m2 v2. This is a total linear momentum of the two objects after the collision. This is the total linear momentum of the two objects before the collision. According to that law of conservation of linear momentum, these two momentum are equal. Yeah. So Pi equal to Pf. Already we saw that is in our elastic collision, total momentum is conserved. So Pi is equal to Pf. So Pi means m1 u1 m2 u2 Pf, sorry, Pf equal to m1 v1 m2 v2. Okay, so m1 e1, we can take m1 v1 into this side, so minus m1 v1 m2 v2. We can take this quantity into here, so minus, because here plus, after crossing that equal, the sign will change. Okay, m2 u2. We can take a note m1 as a common. Okay, m1 mean m1 into u1 minus v1. Here m2 common, so m2 v2 minus u2. So take it down. This is a momentum, simplified form of momentum before and after collision. This is you can label it as something form of equation 1 or 2, because it will use later. Okay. Now we are going to the kinetic energy. Okay. This is a momentum, and now we are going into that kinetic energy equation. Kinetic energy means half mv square. Okay. Before collision, kinetic energy, total kinetic energy, and after collision, total energy will same. Yeah. So before collision, mass m1, it kinetic energy mass m1. So ke m1. Okay, which is equal to half mass into velocity by 2. So m1 e1 square. Yeah. For m2 object, kinetic energy means m2. Okay, half m2 u2 square. Okay, this is the kinetic energy before collision for this m2 object. This is the kinetic energy before collision for this object. After collision, their velocity changes. So after collision, kinetic energy changes. So m1 v1 square ke m2 half m2 v2 square. Okay. For elastic collision, these two kinetic energy will equal. That means, so total. Okay. This is the total. This is the total. Total kinetic energy before collision, which is equal to total kinetic energy after collision. So note it down. Okay. I can put it here now. Half m1 u1 square. Why sir added the kinetic energy? This is a system. In system, there are two objects. One object has something kinetic energy, and another object has a something kinetic energy. In order to calculate what will happen, you have to convert it. You can calculate their total kinetic energy before collision and after collision for the two objects, because that contains one system. Okay, two objects. So kinetic energy added, momentum is added for the calculations, because that object belongs to one system. Because for the collision, you need two objects. Okay, so of m1 u square and of m2 u2 square, which is before collision, and after collision, which is equal to after collision. Right? We can cancel out off because taken into common and cancel out. Okay, so cancel. Of cancel. Now take this quantity into here and take this quantity into here. So m1 u1 square minus m1 v1 square, which is equal to m2 v2 square minus this quantity. Okay, we can take in the m1 as common. So u1 square minus v1 square, which is equal to m2 taken out common m2. Okay, so v2 square minus u2 square. We can recalculate a square minus b square formula. A square minus b square formula. A square minus b square means a plus b into a minus b. Yeah, a plus b into a minus b. So m1 a plus b, because this is a, this is b. So a plus b u1 plus v1 into a minus b u1 minus v1. Yeah, that formula a square minus b square also apply here. So m2 v2 plus u2 into v2 minus u2. This is a formula for a square minus b square. Okay. Now we can divide this equation by the momentum of that. Already we have a momentum. Yeah, m1 u1. So already we got there. We have here. Okay. Already we have a simplified momentum, that is m1 u1 minus v1 equal to m2 v2 minus u2. Yeah. So divide this equation by divide this equation. Okay, because we don't know what is u1, what is v1, what is v2, u2. So we have to divide this equation by divide this equation. So what will cancel? M1, M1. Okay. So here divide by this quantity. U1 minus V1 cancel out. M2, M2 cancel out. V2 minus E2 cancel out. So we have only this quantity and this quantity. U1 plus V1 is equal to V2 plus U2. I can write it here now. Divide this equation because to know the unknown quantity. Okay. What is the reason for dividing? Because we have to know what is U1 or what is V2 or what is U2. Yeah. So simplified form here. You can take an U2 here. So U2, U1 minus U2 equal to V2 minus V1. We can rewrite the equation because U1 minus U2 which is equal to minus of V1 minus V2. Yeah. Because interchange means we have to put minus sign, so which is the direction opposite means. Okay, this means that this is the initial velocities, this is the final velocities, their differences are equal but in opposite, so minus signs are there. Okay. Okay. So dividing means I already told you to know the unknown quantity because we don't know U1, U2 or V1, V2 in terms of other quantity, but mass is conserved. Mass does not change. So we have to divide. We have to neglect mass. So that only we divide that two equations. Then only we got a simplified form here. Yeah. This means that for elastic head-on collision, the speed of these two bodies, okay, same magnitude, difference, okay, difference means something value equal, but opposite direction, okay. So magnitude same, but in opposite direction. So here also you can calculate what is V1, okay, V1 or V2. Like first of all, in that equation, from this equation, V1 equal to V1 is here, U1 taken into here. Okay. So V2 plus U2 minus U1. This is the formula for V1. In your book, V1 equation is this. Okay. V2 plus U2 minus U1. And V2 from this equation, V2, U2 is going into the here, go into here. So U1 plus V1 minus U2. So this is a equation for unknown quantities, that is V1 and V2. What is V1 and what is V2? V1 is the final velocity of the first object. V2 is the final velocity of the second object in terms of other three quantities. But in this equation, you have to know what is V2. Then only we will convert it into, we will calculate V1. And what is V1 here? Then only we can calculate V2. Okay. So to find the final velocity V1 and V2, so we can like already we have some equation. Okay. This equation. And we can put this V2 equation into like M1 U1 minus V1 because we got this equation M2 V2 minus U2. We can put V2 here. So M1 U1 minus V1 equal to M2 V2 replaced by this U1 plus V1 minus U2 minus U2. Okay. Minus U2 means minus 2U2. Okay. Okay. So we will multiply m1 into u1. So m1 u1, m1 into v1, m1 v1. And as well as here also m2 is multiplied by u1 v1. Okay, I will write it here. m1 u1 minus m1 v1 plus m2 into u1 m2 into v1 m2 into minus 2u2. So m2 into minus 2u2. Okay, right. So this is the process to find the what is v2. Okay, right. m1 u1. We can take that u1 quantity to here. So minus m2 u1. And as well as this quantity goes here. So plus 2 into m2 u2, which is equal to, there is a one quantity here and this quantity goes into here. So m2 u1 plus m1 v1, this object here and this quantity is here. Okay. We can take an m1 as common. So m1 u1 minus, okay, u1 sorry, m2 here. So u1 we can take a common as u1. Okay, u1 m1 minus m2 plus 2 into m2 into 2 u2. Here also we can take an into like m2 v1 and sorry, okay, m2 v1. Okay, sorry, m2 v1 and m1 v1. So we can take an as common as v1. So m1 plus m2 into v1. m1 minus m2 into u1 plus 2 into m2 u2 equal to m1 plus m2 into v1. This is a another one simplified form. For to find the v1, this quantity m1 plus m2 goes here, that is divide here. Okay, so divide means m1 plus m2 by m1 plus m2. Okay, because this quantity goes into here, so we will get for v1 m1 minus m2 u1 m1 plus m2 plus 2 m2 u2 by m1 plus m2. This is a equation for v1. So to find the final velocity of the first object, there is a equation. This, okay. In this equation, you can see there is no unknown quantity. Only known quantity is there. That only we are calculate this type of equations. Okay. In this equation, you can see that there is no v2 because v2 is unknown quantity. But you want known quantity. Before collision, we have to decide what is the velocity. Okay. So u1 is unknown quantity, u2 is unknown quantity. Sorry, u1 is known quantity, u2 is known quantity, m1, m2 known quantity. With help of known quantity, we will calculate the unknown quantity, that is v1. First unknown quantity v1. That is the velocity of the second object. For that, similarly, we can substitute some other equations to find the velocity of second object. Okay. Final velocity of the second object means v2. So we got v1, v2, u2 minus e1. Okay. So we can substitute this equation into, already we gave one equation, that is m1 u1 minus v1 equal to m2 V2 minus U2. Yeah, this is the momentum. And we have a V1 equation. So we can substitute this equation into here. M1 U1 minus V1 replaced by this. So V2 plus U2 minus U1, which is equal to M2 V2 minus U2. Okay. So minus, okay, minus, we can minus of V2 minus of U2 minus into minus plus 2 U1. U1 plus U1. So 2 U1. Okay. These two quantities add up. Okay. 2 U1. M1 2 U1 minus M V2 minus U2 equal to M2 V2 minus U2. We can multiply M1 here. So 2 M1 U1 minus M1 V2 minus M1 U2 equal to, here M2 is multiplied by these quantities. So M2 V2 minus M2 U2. Yeah. So you can calculate what is V2 here. You can later you can simplify it. What is V2 here? Just think about it. Okay. 2 M1 U1 is the here, but M2 U2 goes here. So minus into plus, minus converted into plus. So 2 M1 U1 plus M2 U2. Yeah, minus this quantity is there, M1 U2. Okay, M2 V2 minus sorry, plus, because this quantity will goes here. Okay, so plus M2 V2, right? So in this quantity we can take it as V2 as a common. Yeah. So from this equation we can take a note V2 as a common. So M2 like so sorry, here M1. Yeah, M2 plus M1 common as V2. Okay, so here 2 M1 U1 plus, we can take a note U2 as common. Yeah, so M2 minus M1 into U1 from this here. So U2 common here, V2 common, M1 M2 M2 minus M1. You can change M1 plus M2 because in terms of addition we can interchange. Okay, so to know the V2, this quantity goes here by divide. Yeah, so 2 M1 U1 by M1 plus M2 plus M2 minus M1 into U1 divided by M1 plus M2. So this is the equation for to find the velocity V2. So, okay. So already we have a equation to find the what is unknown quantity of that second object velocity V1, and now we have another one equation for V2. V2 is nothing but which is a final velocity of the second object. Okay, right. So I will show you one simulation regarding that like collision. So in this process, you can see some two objects here. Okay, I will. Okay. So in order to have a collision that U1 and U1 is greater than U2. Okay. So we can put here that is U1 here 1 meter per second and U2 is 0.77. I think really near. Uh, okay, so we can change it to here like 0.5. Okay, there and this will go. We can change into 1.5. Okay, so two objects is there. One object mass is 1.51, and another one object is 1.46. We can change another masses. Okay. Velocity first object which is should be higher than that second object which is more move faster than the second object, so that that only we can put some more value into that velocity of for this first object 1.50, for the two second object 0.50. Momentum means mass into velocity, so mass 1.51, you can multiply and you can check that 1.51 into velocity 1.5, which is equal to 2.265. So we have here 2.26 round off. Okay. For the second object, these are always all belongs to before collision. Okay. For the second object, mass is 1.46 into velocity 0.50. So multiply these two quantities, we can get 0.73. That is momentum. Okay, right. You can see here momentum 2.26 because modulus means directions. Okay, 0.76 velocity modulus mass 1 and 2 1.51 1.46. Okay, kinetic energy. So kinetic energy calculated by the half mv square, and total kinetic energy calculated by the kinetic energy of the individual particle and calculated added up. Okay, so kinetic energy 1.88 joule. These two objects will move now. Okay, so you can see momentum, velocity, kinetic energy, but this is before collision. In elastic collision. Okay, so now the momentum changes. Yeah, because velocity changes. You can see that mass does not change, velocity change. Whenever collision happened, their velocity changes. Yeah, changes. We can verify that. Yeah, and whenever velocity changes, when the momentum will change. So momentum also change 0.78 and 2.22. But you can add, that is before we have some other 0.73, after that 0.78 and 2.22. Yeah, you can add 0.78 plus 2.22. We get 3. But the Fibor collision, because some other value, yeah, that is momentum, some other value, but added up, it also gives 3. So total momentum before collision and after collision does not change. Okay. So here 2.26 before collision momentum of the first object. 2.26. The momentum of the second object is 0.73. We can add 2.26 plus 0.73, 2.99. That is equal to 3. So equal. Okay. So this is a elastic collision. For one elastic collision means that also. Okay. So we can go to here. Okay. Right. So momentum, you can say that momentum, mass into velocity, 1.49 into 3, 4.47, and momentum of for this second of the 0.75 into 1.05, 0.079. Okay, so 4.47 and 0.79. This is the total momentum before collision. And kinetic energy. So kinetic energy is 7.12. Kinetic energy does not change. Yes. Mass of the first object and mass of the second object. Okay. So now these two objects will collide. Okay. So now momentum changes. So momentum is converted into 2.53 and 2.73. 2.53 plus 2.73, 5.26, and here also 5.26. So momentum does not change. That means conserved. This is a uh, case of elastic collision. Okay, so we can check the all the quantities here: kinetic energy and potential. Sorry, momentum. How the momentum is conserved, or how the kinetic energy is conserved. Okay, all the quantities checked by the this simulation. Okay, right. Okay, so class will finish. Anything doubts? Okay, no doubts. So I can finish this class. Jai Bharat, Jai Vidyashakti, Jai Hind. Thank you.